Covering a session on efficient deep neural network inference, right? Uh, can I can I get some confirmation whether my voice is audible? So I'll be discussing some of the algorithms which are used to you know uh, i- which are used to infer the deep neural network efficiently. Okay, so I'll be covering first I'll be covering the algorithms, and then I'll be covering the specific hardware accelerators for deep neural networks for particularly for inference. Okay, so yeah. So as you see in a deep neural network, pipeline. So first you have a training stage, right, and then you have a inference stage, right. So this session is particularly meant for efficient neural network inference. Okay, so yeah. So the first challenge, that you will be facing for deployment or inference is that the model size, right? So the model size is one of the the biggest challenge for deployment of the model on onto your embedded space, platforms, right? Yeah. Uh, then also, you have uh, some other problems also, right? So if you're deploying your models onto your on the cloud, so there is some privacy issues and some latency issues, right? While you're doing while you're deploying your models on the clouds, right? So assume if you are for self-driving cars, uh, the latency is the very much important, right? So for real time inference is very much important. Even every frames per second is very important while you are designing the models for self driving cars and drones, right? So for that purpose, there has to be some techniques, right? So for algorithms to efficiently run the neural networks on the embedded platforms, right? And then you get a maximum accuracy without losing the accuracy, right? So yeah. These are some challenges, right? So as I said, first is a model size, right? So if your model size is very large, then it's very much difficult to deploy your model onto your on your the memory on the embedded platforms, right? So first is memory, right? How do you decrease the size of the deep learning model so that your deep learning model can be fit onto your SRAM cache, right? So to get for fast access, right? And also to reduce the access of DRAM. Instead, you only access the cache instead of going for DRAM for accessing, right? So this is one of the challenge. And then it's the second challenge is the energy efficiency, right? As you see, right? So if you see the energy taking for DRAM is much more than the cache, right? So the energy spent and the time spent for accessing the data from DRAM is much fast, right? So if you are designing any deep learning hardware, so there has to be two parameters you have to look in, right? For first is the data transfer, data access speed, and then next is a storage, right? Efficient storage, where you want to store, where you want to store the data on your processor, right? And then next is a sparse, right? Sparsity, right? So if how you can efficiently compute your matrix multiplication in a sparse way rather than in a dense way, right? So that is one of those are the parameters which you have to look for when you're developing your hardware, right? So uh, yeah. And one thing is that you have to consider the algorithmic perspective also while you are designing your hardware, right? You have to that hardware has to be, adaptive to the algorithms, efficient algorithms for the inference, right? So the hardware, so co-design, hardware algorithmic co-design has to be there for the development of the ecosystem for efficient deep neural network inference, right? So this is the second challenge. And then we'll go with the hardware family, right? So in hardware family, you have two parts, right? One is general purpose, and then another is specialized hardware. So in general purpose, you can see there are two types. One is CPU, and another is GPU, right? So what is CPU, right? CPU is, the cores in the CPU, are much more powerful than the core in than a core in a GPU, right? So the core is, the core in the CPU is like a big elephant, right? So when you compare to the core in a GPU, so the core in GPUs are like ants, and the core in a CPU is in a big elephant, right? So it performs huge, but the number of cores, right? The number of cores in GPU are much more than the number of cores in CPU. So you can see the number of cores like around 10, 20, 50, right? So in CPU, but in GPU you can see 5,000, right? The number of cores, right? So CPU is latency oriented, and GPU is, throughput oriented, right? So when you come to the specialized hardware, so you have FPGA, right? And then you have ASIC, right? So FPGA is, the programmable logic. So it's, it's also very much, flexible. It gives very much flexibility for designing your deploying your models on the FPGA, right? So you assume it will give the it will give the you know 1 second. So it will give the, much more flexibility in terms of the precision, right? So you can assume if your model is, int 8, right? So if you want to design your FPGA with respect to the int 8 precision, right? So and then you the again you can reconfigure for FP16, like if you will not get better performance for int 8, then you can change with the FP16, right? So and then also to FP32, right? So there you have a much more flexibility while you are deploying your models onto your FPGA. And then next will comes with a next comes with a ASIC, right? So ASIC is a fixed architecture, right? So in FPGA, what happens is you can change the architecture of your design, right? So like if you design the hardware today, then you can change, right? However you can modify the it's like a reconfigurable computing, right? You can reconfigure with respect to the models you have. And then you have ASIC, right? So ASIC is a specialized architecture, right? So your TPU is a ASIC, and your the Iris by MIT is a ASIC, right? And EIE by Stanford is a ASIC, right? So these are the specialized chips, you can say, a specialized chip for deep learning, right? Uh, so this ASIC is specifically meant for application specific, right? So if you consider TPU is specifically meant for deep learning, right? So you can't do graphic rendering and other general purpose application onto your ASIC, unlike in GPU you can do general purpose, right? So this is the hardware family you can see nowadays, right? I hope you are understanding. Yeah. So next we'll go with the algorithms for efficient inference, right? First we'll go with the pruning, and we'll see what pruning is, and then next we'll see weight sharing, quantization, and then next we'll see low rank approximation, and then the binary or ternary net, and then the Vinograd transformation, right? So these are efficient, the algorithms, right? The techniques for efficient inference, right? So this low rank approximation, right? So this you can use for both training and inference, right? So for both training and inference, but this you can use for uh, you know uh, for inference only. But you have one feature, right? The quantization aware training in by NVIDIA. Uh, so that is like you can do quantization, in during the training time also, right? The
Okay,
quantization
Darshan.
aware training. Yeah.
Yeah, can we take some questions now?
Okay. Okay. Yeah. Sure.
So, first question is, what is meant by latency? That
Yes.
came before in a previous slide.
Okay. Yeah. So what is latency, right? The response time, what you will get, right? So if you do if you are doing some real time inference, right? So what response time you get from the processor, right? So at what time it will give the result when you give the some computation to the processor. So at what speed it gives the result is called the latency, right? Yeah.
And next question is, DRAM is fast.
Uh, Actually, I can't hear you. So can you repeat it once again? Yeah. I think we can
No,
take the
the
questions. Yeah. Yes.
question is, DRAM is fast or uh, cache?
No, no. Cache is very fast, right? So DRAM is less fast than cache, but the access speed of cache is much more than the access speed of DRAM. So DRAM is slow than cache, right? So it's better, if you compress the model. If you apply the algorithms to compress the model, and then if you deploy on on chip, right? So then it will be fast, right? Because the access speed of the cache is much more than the DRAM, right? Instead of going for DRAM, you store in a you store your model on the cache, so that you'll get a much more speed of access and computation, right?
Okay, next question is, what are the chips which are made by ST Micro for ML execution? Comes under which class?
No, HT micro. No, I don't have any idea about HT microelectronics. But as I said, the Iris, the chip is by MIT, and the EIE accelerator is by Stanford, and there are many other startups, right, which are doing the specialized chip for deep learning, right? So you can see the Habana and other startups, right? So they are doing the specialized chips for deep learning, right? Yeah. I'm not sure about
Next
ST
question is,
microelectronics. Yeah.
uh, help. Sorry.
Yeah. No, I can't hear you. Can you repeat the question?
Now, how quantization helps in inference?
Okay, okay. So what is quantization, right? So quantization, it's a technique, right? So to reduce the number of bits to represent, the number, right? So if you're doing the it's like a, the reducing the precision, right? If you want to reduce the bits, if you want to represent the bits in 16 bit, and if you represent in 8 bits, right? So you'll get the number of bits is reduced, right? So that the model is compressed, right? So if you have less bits to represent, and you can store your deep learning model on your cache, right? So that quantization is basically for the storage perspective, right? The storage perspective. If you do quantization, then your model will be decreased, and you can store your deep learning model on cache, or deploy, or rather than on DRAM, right?
Okay, one more question is here.
Yeah.
If
uh, Actually, I think there is a problem. I can't hear you actually. So yeah, as I was discussing. So these are the different algorithms for efficient inference, right? So one is pruning, one is weight sharing, and low rank approximation, and next is binary or ternary net, and next is vinograd transformation, right? So first we'll do with what pruning, right? So pruning is a technique which is used to remove the less affected connections, right? So while if you remove those less affected connections, so there your computation will be reduced, right? So your computations will be reduced, thereby you'll be getting a lot of speed. Okay. So I'm not sure whether TF Lite, I think TF Lite, they don't have pruning, but I guess in TensorRT, there is a pruning, right? So yeah. So yeah, the what is pruning, right? So as I said, the pruning is a technique which is used to the remove the connections which is less effective, right? So it removes the techniques with less effective, right? So there are some techniques, right? So you can use Taylor series expansion to see which are the weights that are less affected, and by that method you will get to know which are the connections which are less affected, and by removing that, your computations will be reduced, and thereby your accessing your speed will be increased, right? So this is basic intuition behind the pruning. And if you see in your brain also, the pruning will happen. Okay. So while you are small, there will be there will be some amount of connections, but after your yeah, I'll come with, okay, I'll come with this one. Okay. After you become 30 years, right? After 30 years, the number of connections in your brain will be decreased, right? You're pruned. Also, you'll be you know uh, you'll not decrease your thinking, right? So thereby you are not decreasing the accuracy, as I say here, right? So after pruning also, the accuracy will not be reduced. Of course, there will be a small amount of reduction, right? But there's not a gradual decrease with respect to uh, the accuracy, right? So yeah. So if you see the the intuition behind here is that, so this is a line. Okay. So this black line, so this black curve is a line. And the equation of that curve is this one, right? So point zero one x square plus x plus 1 is the equation of this black curve. And then if you remove this floating point operation, right? So your line will be the kind of this one, right? The red line. So there will not there's not much difference between the curve and the line, right? So yeah, so this is basic intuition of the pruning. So there you are not decreasing uh, the accuracy of that is what I mean to say, right? So if you see the connections, right? So this is the the number of connections which is there before the pruning, and after pruning, the number of connections is decreased by 10x, right? So there, this is for LXNet. Okay, so before pruning, you have 60 million connections, and after pruning you have 6 million connections, right? So thereby you are decreasing the number of connections and the computations. Thereby you are decreasing the latency, and you are increasing the throughput, and then you are increasing the speed of computation, right? So this is one of the interesting technique for compression, right? So another thing is to note is that if you only train the network, you will not get that much of a compression rate, right? If you compare to the accuracy, you have to prune, then retrain, prune, then retrain, right? So to get your model accuracy better, and then you'll be getting you know you'll be getting a good amount of a compression rate, right? While comparing to the accuracy. So yeah, so this is one of the uh, the pruning retraining, how it will how it will make your compression rate better, comparing only the pruning method, right? So this is what the pruning method, right? So if you do only pruning, okay, so you'll not get that much amount of compression rate. But if you do pruning retraining, right? So you'll get increased amount of compression rate. So you'll remove the parameters more, and then you'll get more compression rate without losing more accuracy. Okay, so and also if you iteratively prune and retrain, right? So pruning retraining, right? So then you'll be getting more amount of compression rate by removing more number of parameters in your neural network, right? So this is only for inference, right? So this is not for training, right? As you see here, train connectivity, and then you prune the connection, right? After training, you prune the connections, and then you train again the weights. So thereby you'll be getting uh, more compression rate by removing more number of parameters in your neural networks. Yeah. So if you see the blue score of pruning the RNN and LSTM, so if you see here, right? So this is only with a pruning, right? So and this is the pruning and retraining, right? So this is this one, right? The green is pruning and retraining, right? So you're getting with respect to the pruning and retraining, you're getting the prune weights, right? The number of percentage of prune weights is more, right? While you are doing the pruning and retraining, right? Compared to the only the pruning, right? So there you are getting more the compression rate. So if you see the result of if you see the result of the pruning and the pruning of the image captioning, right? So if you see, you are compressing around 90% on all of this, right? So if you see the image captioning result of the original and with respect to the prune 90% network, so it's almost same, right? So if you read it carefully, right, of this image, right? So the result is not much uh, you know the degraded, right? When you prune the network of by 90%, right? So if you read here, right? So the basketball player in white uniform is playing with a ball, right? So and the basketball player in a white uniform is playing with a basketball, right? So yeah, so there you are not decreasing any accuracy, right? If you see here also, right? You're not decreasing any accuracy. But if you are pruning, you have to be careful with with what amount of pruning you are doing, right? So accuracy will gradually decrease at some point, right? If you are here, you are pruning 90%. At 91% it may go gradually decrease, right? At 91% of pruning, your accuracy will be gradually decreasing, as I shown in the previous slide, right? So you have to be careful while you are implementing any pruning on your neural networks and all. So yeah, here if you see here, right? So this is a cutoff point of pruning, right? So this is a cutoff point of pruning. So if you do more than this one, so you'll be getting uh, gradual decrease in the amount of accuracy, right? So you have to be careful with the cutoff point of pruning. Yeah. So as I said, right, in human brain also pruning mechanism is happening, right? When you are newborn, right? So you have a 50 trillion synapses, and while you are one year or some 2 year old, you will be having the 1,000 trillion synapses, and after you become some adolescent, you'll be having 500 trillion synapses. So you are decreasing the synapses, right? The connection is decreasing, but your thinking ability and decision making is not it's not decreasing, right? So it's increasing, but it's not decreasing, right? So this is the pruning happening in your human brain also, right? Yeah. So this pruning will actually change the weight distribution happening, right? So before pruning, your weight distribution will be same as like this one, and after pruning it will be like this one, right? And after pruning and retraining, you will be having a uniform distribution, right? So you'll be having between here. So this is the area where you have a less affected weights, right? So you prune away the weights, and then see here, right? So here these are less affected, but the the count is more, right? So if you prune away those less affected weights, so you will gradually have a less connections, thereby you are increasing the number of the speed and the throughput, right? You are reducing the latency. Yeah. So and then we'll come with a weight sharing. Okay, so what is weight sharing, right? So weight sharing mechanism is, you have a number of floating points, right? So why you consider this thing, right? So you just represent these whole numbers with only two, right? With only two, right? So it's not decreasing any the accuracy. Okay, so you are just converting the floating point operation right here into the integer, so thereby the number of bits to represent the numbers will go down, and you're decreasing your model size, and you can store onto your on chip memory rather than going for DRAM, right? So this is one of the intuition behind weight sharing, right? You are going back from you are going from floating point operation into the integer, right? Yeah. So this is the weight distribution before the after pruning and before quantization, the weight sharing, and then after quantization you'll get the discrete weights, right? So you'll be getting discrete weights, right? So you are having only this amount of weights, right? Thereby you are not having the weights here, right? So thereby the bits represent will go the bits used to represent will go down, right? So this is the weight distribution happening after pruning and after quantization, right? So this is the one of the so this is one of the technique happening here, right? Yeah. Yeah, yeah. How many bits do we need to represent? Okay. So if you see here, right? If you see here, when it comes to the convolution neural networks, the number of bits, right, required is only four, right? When you compare to the fully connected layers, is only the two bits, right? So you have to be careful, right? How many number of bits you can you can use to represent, right? If you use for convolution layers, if you use below 4 bits, then your accuracy will be gradually decreasing, right? So you have to be, so this is a cutoff to represent the this is a cutoff for number of bits to represent, right, in convolution. And this is a cutoff to represent the number in to represent number in the fully connected layers, right? Uh, yeah. So yeah, so this is the the number of bits we need to represent. Okay. Yeah. So and you can see here, right, the compression rate combine with the pruning and weight sharing. Okay. So if you do the pruning only here, right, so your compression rate is less, and if you do with the pruning and quantization, you will get more number of compression rate when you compare to only pruning. Okay. Yeah. So this is a result of pruning and weight sharing working together, right? So this is a graph which is representing the accuracy loss with respect to the compression rate, right? If you do if you combine the pruning and quantization, you'll get better result when you compare to only pruning, right? And other techniques like only quantization and only the SVD, right? And another technique used for efficient inference is Huffman coding, right? As you know, in Huffman coding, yeah.
So some questions I sent you on chat. Kindly check on GoToWebinar chat. A couple
Okay,
of
okay.
questions.
Can I finish until I check?
Sure, sure.
Yeah, yeah. Yeah. So this is the Huffman coding, right? So this is the technique which is used for efficient inference also, right? So rather than yeah, represent in the bits, like you represent in the term which is Huffman, through Huffman coding, right? What Huffman coding will do is that for infrequent weights, right, use more bits to represent, right? For frequent weight, you use a less number of bits to represent, thereby your number of bits will to represent will go down, and you will have an efficient way to represent a number without losing the accuracy, right? This is the technique used for many compression technique, right? So you can see in video compression and in audio compression also, this kind of technique is used, right? Huffman coding, right? uh, so Huffman coding is now used uh, for compressing the deep neural networks. Okay. This is the summary of deep compression. Okay, the deep compression in the sense, the three techniques which are used, right, which are used to compress the model, right? So this is for pruning, and this is for quantization, and this is for the Huffman encoding, right? So in pruning, you will train and and then you again iteratively prune, retrain to get less to get you know to get more compression rate. And if you see the quantization, right, so you will have less bits to represent for the number, and for Huffman coding, you will use more bits for more bits to represent for infrequent number of weights, and less bits to represent for frequent number of weights, right? So this is the summary of the previous techniques I discussed. And if you see here, right, so this is the result of the compression ratio. Okay. So what it tells is that if you use a deep compression, right, the three algorithms. So what happens is your original the size is 1070 kb. Okay. And after deep compression, you will get this much amount of size of your model. Okay. As if you see here, right, your 44.6 MB is converted to 4 MB, right, after deep compression, right. Same as like this, right. So the Google net, right. So this is a compression rate, and this is a compression size. Okay. So here you are getting 40x, 39x. So this is a model dependent, right. One model can be efficiently, you can you can the result of the deep compression will be better for some models, and the result may be better for for some models, right. It can be like as you see here, right. You are getting around 11x compression rate. As you see for Linet, you are getting more compression rate, right. But you are not decreasing the accuracy is almost same, right. Why you are this SqueezeNet, right? So let me introduce what SqueezeNet is, right? So instead of implementing the implementing the deep compression algorithms, why can't you design the network which is which is already compressed, right, which is already compressed? Why can't you you design a network which is already compressed, instead of applying the compression rate, right. So without losing the accuracy, right. Yeah, so this is the SqueezeNet. You know SqueezeNet is a network which is for image processing, right. So this you can use for image computer vision with less accurate with less decrease in accuracy, by and you are gaining the more compression rate, right. And if you apply again deep compression on this SqueezeNet, you will get around 100 200x compression rate, right. As you see in the next slide, we'll see the compression rate, right. So this is a SqueezeNet. Before applying deep compression, your size is around 4.8 MB, right. But if you see here, after applying the deep compression on the SqueezeNet, your model size is around zero point 0.5 MB, right. So this is the result of applying the deep compression on your SqueezeNet, right. So before applying the deep compression on your SqueezeNet, your model size is around 4.8 MB, and after deep compression will be getting 0.47 MB, right. Yeah. So let me go ahead with the questions I got. Yeah.
No,
Yeah.
I sent you all the questions in GoToWebinar chat. Just check the
Okay.
GoToWebinar chat.
Okay. Okay.
Okay.
Okay. So yeah. Yeah. Uh, okay. This I think has been. Okay, so this was just a notion, right? So to understand the weight the weight sharing. Okay, I mean the pruning. Okay, so the pruning, right? You are saying with respect to the pruning, right? So the question is how does removing the less affected term from the equation of curve translation to the number to the number of neurons in the models, right? So yeah, this was just a correlation, right? So as I explained in this one, so this was just a correlation, right? I was giving, I was just correlating how the removing this part of the equation will be not affecting, right? So as you see here, right, the equation of line and the equation the line and the curve is almost same, right? But here you are losing some amount of accuracy, but it's almost same. But here you are decreasing the floating point operation, right? The floating point operation, you are only doing x plus 1 instead of this quadratic equation, right? Yeah. Do you show how this be achieved in the code? Okay. So this actually we will cover in the detail in the course, but in this session I didn't cover about the implementing in the code, uh, and then which is the best library or repos to implement all these techniques. Okay. This actually these are done by the libraries by which have their own hardware, right? So you have HT Microelectronics as they have their own they have their own frameworks in which these techniques have been used, and you have TF Lite in which these techniques have been used, and TensorRT, right? And then you have Qualcomm API, where these techniques have been used, right? Yeah, I feel quantization. Yeah, so quantization, it's a technique which is used in almost all the frameworks, right? When they are building the API for inference, so the first thing, the first algorithm they have to target is for the quantization, right? So this is the first go-to the technique for implementing uh, for developing their efficient neural network inference API. So they have to go to first is a quantization, right? How Huffman coding reduce the deep compression, right? So yeah, how Huffman coding, yeah. So you have this Huffman coding, you can see here, right? So you can study, you can study it in your BTech, right? Or in other courses, right? So this Huffman coding is used for video compression, right? But how it reduced, right? So you're reducing the number of the number of bits to represent for more frequent number of weights, right? More frequent number of weights, you're decreasing the amount of the amount of bits to represent, you are decreasing, right? While you compare with the original model, right? Is compression shown in your PPT? Pruning is a pipeline Huffman coding. No. These actually, these are model dependent, right? So this actually, these three technique, if you combine with these three technique, combining these three technique will work very good for some models, right? And when it compared to the other models, right? So if you check with the you know. In the model zoo, right? In TensorFlow hub, right? So you can see, not these techniques are not used for all the models, all the neural networks, right? Okay, so what is top one and what is top five accuracy? Okay, so let me go with that. Okay. So the top one and top five accuracy, right? So yeah, this was actually I was figuring out the top one and top five. I think I'll let you know once. No, I'll I'll, uh, I'll confirm. Okay. So are there any questions I can?
I, that's all for now. You can continue.
Okay, okay. So next, we'll go with low rank approximation. Okay. So what is low rank approximation? Uh, so uh, so low rank approximation is a technique, which is also used for deep learning training also, and also for deep learning inference also. Uh, yeah. So in low rank approximation, what happens is you're dividing the complex neural the complex neural network into two smaller subnetworks, right. You have if you are used if you are familiar with the PCA, right, the principal component analysis. You can see the singular value decomposition used there, right. So the singular value decomposition is you are splitting the complex into the two simpler matrices where there will be the less computation, right. After you reduce the small matrix, the big matrix into the two small matrix, your computation will be reduced, right. I think you can see the in PCA, the SVD, singular value decomposition, has been used, right. So here also singular value decomposition used for the eigen vectors, right. So those concepts will be coming in your singular value decomposition, right. So this is for yeah, so this is mainly used for convolutional neural network. Okay, so yeah, so this is mainly used for convolutional neural network. Yeah. And also I think SVD, only SVD is not used. There are some other techniques. I was reading, I think some paper, I think I forgot the name. I think there is some name called TC, I think the short form. So that is also one technique used for it's same as like singular value decomposition, but for in your while you're doing matrix, right, for deep learning, you will be having more dimension, right. You are having the tensor, right. So tensors, right. So those are very high dimensional. So there, if you want to apply the low rank approximation, there you have to they have come up with some other techniques like singular value decomposition for decomposing the complex neural network into the two simpler network, right. Yeah, so this is the low rank approximation for fully connected layer, right. So here you are decomposing the weight matrix into the to the simpler matrix, right. The simpler matrix, thereby you are reducing the number of computations. Okay. So this is for per layer basis. Okay, this is for per layer basis, not for full network, right. Yeah, yeah. Next we'll go with a binary or a ternary net. Okay, so this is also one of the technique, right. So for efficient neural network inference, right. So the binary or ternary net is that in binary net, what happens is you are representing the number only in 2 bits. Okay, only in zero or in 0 and 1. But in ternary net you have 3 bits to represent. Okay, so if you see with the int 8 and this binary or ternary net, there in int 8 you are representing 8 you are representing the number you are representing the number sorry, you are representing the number with 8 bits, right, while you are doing int 8. But while you are doing the binary or ternary net, you are only using the 2 bits or 3 bits to represent it, right. So thereby you are decreasing the computation, right. and also the storage. But I think the accuracy will be go down, okay, while you are doing the binary or ternary net. You are only using 3 bits to represent, so that your accuracy will be little bit down, uh, well, compared to the other previous techniques you had seen, right? So this is one of the technique. It will gradually decrease the size of the model and the computations. But if you see with accuracy, it's a bit reduced, right, when you compare to the other models, right? Yeah, next is next we will go with the vinograd transformation, right? So if you see with a convolution, right? So convolution is a heavy compute intensive task, right? So there you have filters, and you have an image, so you have to slide and you have to multiply, accumulate, right? uh, uh, right. So then there you have a lot of computations going on in your convolutions, right? So what do you do in to decrease the number of computation is that you use the vinograd transformation, right? So what is the basic intuition is that, so you have a four matrix, right? The 4 into 4 image, right? So and you have a 3 into 3 filter. So you transform this matrix into the to some to some representation, right? FFT, or like you have FFT and other techniques, right, to represent in some other domain. There in this one you represent in other domain. Thereby what happens is, you'll get the output like this one, okay, 4 into 4, 4 into 4, after applying the transformation. But here what happens is that you are, instead of doing the sliding and multiply accumulating, you're doing only the point wise multiplication, right? So here point wise, this into this and this into this, right? And this into this, right? And this into this, no need the sliding and multiply accumulate, right? Here you are doing the only the point wise multiplication. Then you'll get the result like this, right? And then you change, you inverse transform the transformation what you done here, right? The same inverse transform you do for this output, then you will get the output as like this, right? The same output uh, uh, while you do the convolution, right? The native approach, right? The convolution native approach, you do like this, the same result you will get like this one. But here you're reducing the computation, right? You are bringing the image to some transformation and filter to some transformation, and here you are doing the point was multiplication, right? So there you are here you are decreasing the number of computation while you're compared to the native approach, right? So this was used in NVIDIA devices, right? So in NVIDIA APIs, so this in Vinograd, in Kudinin and your Tensorati, they have used this Vinograd convolution, right? So this is efficient for to implementation of the convolution. So next, we'll see if you see with the speed up of the Vinograd convolution. So here in Kudian 3, it was not implemented. Okay, in Kudian 3 it was not implemented, and in Kudian 5, the Vinograd has been implemented. So here, if you can see here, right? So you're getting the gradual amount of speed up if you take the Kudian 5, where the Vinograd transformation is implemented, right? So this is the performance improvement graph. If you can see the result of the Vinograd convolution, right? Yeah. Next, we'll
So
go with
Darshan, there are many questions. Whenever you're ready, you can answer.
okay, okay. So yeah. Yeah. Let me. Can I complete this hardware?
Yes, yes, sure.
Only. Okay, okay, thank you. So, yeah, so next we'll go with hardware for efficient inference. Okay, so these are all the ASICs, right? The application specific, only meant for deep learning computation. Okay, so what happens here is that while you're designing your own hardware, you have to uh, take into consideration for some target. Okay, some target, right? So, you have to keep one goal as while you're designing your hardware, the access, the access, right? And the data reuse, right? Access in the sense that you reduce the access of a DRAM, and you increase the access of you increase the access of the on chip, right? Like that way, that is one kind of a goal. And another kind of a goal is that you store the deep learning model on chip only, right? On chip only. And another thing is that you do the less precision, right? So this uses the intent, this only TPU only uses the intent, precision mode, right? So there you are getting a huge amount of speed, uh, and then you are decreasing the number of bits to represent, right? So this was one of the target goal, right? So the 8 bit and the precision, right? And for EIE, efficient inference engine, by Stanford, what was happening is that so this they considered, their goal was for sparsity, right? uh, I think you'll be familiar with what is sparsity and how it works, right? So sparsity means there is a lot of zeros, and instead of doing the multiplication for zero also, you just remove that zeros, and you only compute the non-zero values, right? So that is what the sparsity happening, right? So I think I explained the sparsity, and how the at the bottom level, the matrix level, how the sparsity will be happening when you see at the bottom matrix multiplication level, right? So, and then this was the other chip by China Academy of Science. So this was also the specific application specific integrated circuit for deep learning, right? So yeah, so this is how the Google TPU looks, right? Looks like, right? So they have a huge, they have dedicated the huge this engine for matrix multiply unit, right? Though they here you there here the matrix multiplication is happening, right? And then they have a huge on-chip memory bus here, and then if you see the this ASIC, right? This TPU will consume less power when you compare to GPU, right? GPU The GPU in GPU, what happens is, instead of the 30 GBps, right? They have memory bandwidth like HBM. They are using HBM, right? In recent Ampere, Volta, and Turing, they're using HBM version 2 high bandwidth memory. There you will get 900 Gbps instead of 30 Gbps here. There you are getting 900 Gbps, right? So that is very huge, access memory bandwidth, right? So there you will get a lot of speed in terms of memory access. Speed, okay, rather than the TPU. Here the TPU you have a less speed, okay, the 30 Gbps, right? So this is one of the disadvantage of TPU here. And advantage is that you have less you know uh, power consumed, right? So if you see here, right, the matrix unit, so what is happening here is, in one single clock cycle, the 65K floating point operation has been happening in the matrix multiply unit, right? So here here, sorry, it's 64 or 65 kilo of 65,000 65K flops per second per clock cycle is happening in this unit, right? So that is very huge, right? That is also with respect to 8 bit, right? Not a 16 bit or 32 bit. It's only for 8 bit, right? and you have a frequency of 70, the clock rate of 700 megahertz, right? And the peak throughput is 92 tera operations per second, right? The peak throughput, right? So it is around 92 teraflops, right? And then if you see the there is a 24 I think MB of on-chip unified buffer, right? So this is the 24 MB, right? And then the memory bandwidth is not that much high, so that is one of the disadvantage in the TPU. And then if you consider the power, so there you know uh, the TPU wins when it compares to the GPU. It's very much difficult to benchmark the GPU versus TPU, because for some model and some amount of data set, your TPU works better, and some other models like some other models, your GPU works very good, right, when it compared to TPU. And some other batch size, your TPU works well compared to the GPU, right? So it's very difficult, right? So there is one paper, right, benchmarking CPU, GPU, and TPU for deep learning. You can go and read that. That is a very nice paper I had read. uh, there you will get, right. So they have created the one their own platform to benchmark this hardware, right. So they have very well explained all the results they got. So you can have a look at that for benchmarking, right. So this is the TPU, what's the the performance with respect to the CPU and GPU, right? So if you see with the power, right, you are having less power usage when you compare to the when you compare to the GPU and CPU, right? So CPU is consuming more power than the TPU, right? So TPU is consuming less power, right? Uh, yeah, so this actually the comparison between CPU, GPU, TPU, with respect to the power and the watts, how much power it's taking, and the memory bandwidth, right? So the memory bandwidth is very less, in your the TPU. I said, right, the 900, but it's in Volta, right? Volta, there is huge amount of memory bandwidth, so they are using high bandwidth memory. But if you see with the Kepler's, right? So this is Kepler NVIDIA GPU. There they'll be using DDR, right? So they are using DDR memory. So DDR memory has less bandwidth when it compared to the high bandwidth memory, right? So in high bandwidth memory also, they are doing some research on I mean, the increasing the bandwidth, right? So that is also one kind of hardware research going on. So that high bandwidth memory, that is also coming up with versions, right? So you have high bandwidth memory 1 and high bandwidth memory 2, HBM1, HBM2. And then also in DDR also you have versions, right? So GDDR version 1, some versions are there, right? So they are so that is the upgradation. Okay. So this is what I explained. Let me have a quick revision of what I explained. So I covered with the challenges. The challenges are there for inferencing, particularly with respect to the model size and the amount of power utilization. And then I explained with the hardware family, the general purpose and the specific application specific chips, and then I went on through the algorithms, right. First is pruning, and then we discussed about weight sharing, and then we discussed about low rank approximation, right. So you are applying your SVD or some other technique to decompose your complex matrix into the two simple matrix. Thereby you are you're reducing the number of operations, right? And then we also discussed the binary or ternary net. I think I didn't much covered about binary and ternary net. So what happens in binary and ternary net is that the there at the back end, you will have a XOR operation, right? So you have a XOR operation, which will be doing the multiplication, right? So multiplication is equivalent to the XNOR, okay, in the binary net, okay, in binary net, right? In if you see Xilinx, right? So they have the framework, right? So the framework called Fin is a framework they are using for particularly for binary network, right? That is through high level synthesis, okay. So you can use that Fin framework for for binary network, for binary neural network, okay. So that will at the back end, that will use the Xilinx DPU, deep learning processing unit, and then it will increase the speed, okay. And then after the binary or ternary net, I discussed about the Vinograd transformation, okay. So Vinograd transformation is the it's a you are representing the matrix in some different in different space, right? So in different space, thereby you are reducing the number of multiplication, right? So while in native convolution, what was happening is that you slide multiply, right? So there you were having a lot of multiplication addition, okay. But when you see in but when you see in Vinograd transformation, you'll be having your multiplication, you are only doing the pointwise multiplication, okay. So thereby you are decreasing the multiplication, right? So the computation, right, the operations required for computing the convolution, right? But the result is same, but the implementation is different, right? So instead of doing the sliding multiplication addition, you are doing only the pointwise multiplication by bringing that into some different space, okay. Then we discussed, we spent a small amount of time on the specialized hardware architecture, right? I just introduced about GPU, sorry, TPU, about the architecture, and then about the different specification, right, with respect to uh, the amount of power and the flops, right, and the multiplication unit inside that one, right? Yeah. So that ends this session, and I'll go ahead with the questions, right? So let me go ahead with the questions here. Okay. Thanks for answering this top five and top one. Okay. So top five. If your predicted result is ranked descending by probabilities, and if the ground truth is among top five of them, then you. Okay. So yeah, this is the right answer, right? So the top five accuracies, if you predict the result, okay. If you predict the results, okay, and you have a the different probabilities, okay, of prediction, then you take the top five amount, top five, okay, for accuracy benchmarking, right? Okay, so isn't a low rank approximation uh, of convolution is very similar to what is done in mobile net, the filter decomposition part? Yeah, I think, yeah. So that's the main notion, okay. So your you're decomposing the weight matrix, okay, into two simple matrix, thereby you're decreasing uh, the amount of the multiply and accumulate, okay, operations. So there are multiple techniques for efficient inference. Are there any guidelines on when to apply these techniques? Okay. So yeah, so this is a trial and error approach. Okay, so you have to try for for this, applying these techniques for different for different models, and then you have to check whether that particular that particular algorithm is best or for best for that particular model. So you have to see all the techniques, okay. So some may, but I think the quantization is works for all, works good for all the neural networks. So the pruning and other techniques I said, the vinograd is for only for the convolution, okay. Vinograd is for only the convolution, as you know. And yeah, so won't the image suffer a loss in information since we are compressing it to match filter size? Okay, so I mean the image is not suffering. Okay, so you are bringing your filter size same as a image. Okay, so there you are not compressing any image, right? So you are bringing your filter size same as the image size, right? By applying the transformation. Okay, I think yeah, here, right. So you are bringing the filter the size same as the image size, so yeah. Do we need to put the vinaigrette in all the layers? Okay, yeah. So that's vinaigrette. You can use it for all the layers. Okay, but for particular layers, okay, some implementation is it's layer dependent. Okay, some this vinaigrette may perform very good for particular layer, and your Fourier transformation will be good for the next layer, right? And then some other implementation may work good for other layer, right? Uh, so that is all. That is all. The architectural dependent, okay. What architecture, what target hardware you have at the bottom, right. So this it's all architectural dependent, right. Okay, so benchmarking the hardware, right? So yeah, the paper name, right? So I'll say the benchmarking, benchmarking CPU, GPU, and TPU for deep learning. Okay, so you can check, you can type this one, and you'll get the archive paper, right? What is a framework for binary networks, right? Right. While you're doing with a FPGA, there's a framework called fin, okay. FINN, okay. Fin, you can search, right. So fin is a framework for binary neural network, particularly meant for FPGA, right. So the DPU, so DPU is a hardware uh, built by Xilinx on uh, so on that hardware you can implement this fin you can you can use that hardware to do the binary neural network, right, through the fin framework, okay. Fin framework, I'll do one session on the fin on the binary neural network. So yeah, can we expect a hands-on session on? Yeah, yeah, yeah. We'll do the workshop on regarding this one. So we'll do hands-on session on in the near future. Okay. Uh, yes, yes. You can apply all as I said, right? So I didn't apply all the algorithms. I only worked with pruning and quantization. I also didn't work with Huffman coding, right? So I'm not sure whether if you implement all these techniques, it may work good or not. Because okay. So of course your speed will be increasing. Of course you are reducing the latency and you are increasing the speed, but you have to take the accuracy into consideration, right? So deep learning is all about accuracy, right? So that comes the first priority while you are implementing this one. Of course, if you implement all these one, right, you will gradually your speed up will be increasing, and your size will be decreasing, right? But the amount of the accuracy, right? So accuracy is the main priority, right? Compared to the compressing the model or any other technique, efficient technique. So first comes with accuracy when it comes to deep learning, right? So you have to take care of accuracy while you are implementing these algorithms, right? Yeah. So there are many GitHub repos on deep compression in if anyone is yeah. So deep learning, yeah, deep compression by Songan, right? So you can search for deep compression GitHub repo, but I think the deep compression they only used for specific application for specific network, right? So they you will get only for AlexNet, I think, and SqueezeNet, but he didn't he didn't release it for all the network. So that works only for cafe. Okay. That repo will work only for cafe framework, not for TensorFlow, right? If your model is if you're trained on cafe framework. Okay.
Uh, okay, audience, any other questions? So, Darshan, do we have more or are we done for the day?
Yeah, it's done for the day, actually.
Okay. Audience,
So
any final questions for Darshan here? Uh, okay, so thanks a lot, Darshan. Excellent
yeah,
session, very exhaustive.
yeah,
Uh,
thank you.
and thanks, audience, for attending. We'll see you in our future webinars and look forward to more sessions from Darshan as well.
Yeah,
Uh,
yeah. Are there